My name is Bob McNabb. I'm a lecturer here in the School of Geography and Environmental Sciences, and my talk this afternoon is going to be about using space cameras to study big bits of ice and snow, and I will probably mention some other things as well. So, this is a Landsat image of the Malaspina or Sit Plain Glacier in Alaska. This is one of my favorite glaciers to show satellite images of because it is absolutely astonishing to look at. This is a very big Piedmont lobe flowing out of the St. Elias Mountains down towards the Gulf of Alaska at the bottom here. But what makes this a glacier? So I need someone to tell me their favorite definition that they were just thinking of.
A river of ice.
A river of, oh, that's a good one. I like that. Does anyone have a better one?
Yeah.
All right, we'll stick with river of ice. So that actually covers most of what I wanted to say. A glacier is a mass of snow and ice that moves under its own weight. That's the most important part, is that it is actually moving down the mountain. And we can tell that looking at the Malaspina Glacier here, because we can see all of these amazing flow bands that have formed as it has pulsed flowing down out of the mountains. So if we were to take all of the glaciers in the world and melt them and add that to sea level rise, that would, oh sorry, I'm skipping ahead, terrible. So just to give an idea of scale here, if we were to put Coleraine up here in the neck of the glacier as it's flowing down here, Derry would be down here by the coast. So this is an absolutely enormous glacier. But if we were to take all of the glaciers in the world and melt them, we would add about 25 centimeters to global sea level. So that's the acronym here, SLE, stands for sea level equivalent. And again, this is just where we take a mass of water, we spread it out over the current area, surface area of the ocean, and that height then tells us about how much sea level would rise, again, assuming that the area doesn't change. So those are glaciers. Ice sheets are glaciers on a continental scale. So they're glaciers that typically occupy at least 50,000 or so square kilometers. And of course, right now we have two ice sheets in Antarctica, the West Antarctic ice sheet and the East Antarctic ice sheet. And if we were to totally melt both of those, we would add about 65 meters to global sea level. So this is an entirely different order of magnitude compared to the mountain glaciers that I'm going to be focusing on. Similarly with Greenland, if we were to melt the entire Greenland ice sheet, we would add about 7 meters to global sea level. But we're going to be focusing on the mountain glaciers, so these are the glaciers that are not connected to the Greenland or Antarctic ice sheets. And so, when we want to look at how climate or weather is impacting glaciers, one of the things that we go out and do is we actually can measure melt and snowfall using what we call mass balance stakes. So these are just big metal poles that we drill down into the glacier, we let them freeze in, we come back later and we see what the height of that pole is above the surface of the glacier, and that tells us how much has melted away. It looks kind of like this. So this is a figure taken by Matthias Huss, who's a glaciologist in Switzerland. This is at the Greater Aletsch Glacier in Switzerland, which is, I think, the largest glacier in Europe. And this was last summer showing the amount of melt that had taken place over the summer. So at the beginning of the melt season, the top of that pole was actually in the glacier. And by the end of the summer, there was that much melt that had happened at this location. Typically, we go out and we measure these 1 to 2 times a year. So we go out in the spring and we measure what the height is at that time, and that gives us an idea of how much snow has fallen over the course of the winter. And then we come back at the end of the summer, or as close as we can get to it, and we see how much has melted away. Now, we also have automated instruments that we can use to actually measure that height, so we can see what it looks like throughout the year. And in fact, we have a number of these on different glaciers around Switzerland. So this example is from the Gries Glacier, which is another small glacier in Switzerland, only about 5 square kilometers or so. But what you can see, so the red line here is the glacier mass balance, so the difference between the amount of snow that fell during the winter and the amount of melt that took place over the summer. So this is the mass balance throughout the year. Last year in 2022, which I'm sure you all remember, was extremely hot. There were drought conditions over much of Europe. It was very warm in the mountains. There was a lot of melt, and in fact, there was so much melt that happened that we actually had to extend the y-axis of this plot. If you're interested in the statistics, this is about 4 standard deviations away from the 2011 to 2021 mean. It was extremely bad year for glaciers in Central Europe, and we will come back to that idea. The problem, though, is that glaciers are really big, right? We saw the example of the Malaspina Glacier on the previous slide, and so if we wanted to go out and measure Malaspina in this way, it would be very difficult. It would take a lot of effort just to get to the locations that we would want to put mass balance stakes in. So we need to look at another way. Globally, there are about 700,000 square kilometers of glaciers, and they range in size from a few hundred square meters all the way up to thousands of square kilometers. So there's a huge size range. So we can't just go out and measure them like this. We need to use something else. And that brings me to the second part of my title, which is actually the first, and that is space cameras. So we're using remote sensing, which is studying an object without actually going out to touch it, so that we can, usually so that we can do this at scale, right? So we have satellites that are taking pictures over the entire Earth. We can see how things are changing. We don't have to go out and measure them individually on the ground. So most often we're doing this using electromagnetic radiation or light, and we need a source of electromagnetic radiation or light. And so very often what we're looking at is actually the sun. So the sun is emitting electromagnetic radiation. It reflects off of the surface of the Earth. It comes back to a satellite. We measure how much is reflected, and that allows us to see what's going on. We can also measure the electromagnetic radiation that is emitted by the object or by the surface of the Earth, because everything that has a temperature above absolute zero emits some form of electromagnetic radiation, and so we end up with that way of measuring this as well. This is called passive remote sensing because we're using a source of radiation that is not actually the sensor that we are using to measure the radiation. But we can also use the sensor itself. So we have sensors that send out electromagnetic radiation, and they measure what is reflected back, and that's known as active remote sensing. So this is a timeline that shows the different Earth observation satellites over time, starting with the launch of Landsat-1 in about 1972, moving up until today. This is a selection. There's actually a lot more things that are not shown here, such as declassified reconnaissance imagery. So these are all of the spy satellites that the American and Soviet governments were sending up during the 60s, 70s, and 80s. The Americans have declassified a number of these different missions, and so we have images going back, again, to the early 1960s that show that we can use to actually see a lot more changes than just what we've got from these other missions. I also haven't included sensors that aren't cameras, so these are things like laser or radar altimeters that are measuring the height of the Earth's surface from a satellite. There are also synthetic aperture radar or radar satellites. I haven't included these here. That the list would go probably through to the next floor if I did that. And then I also haven't included aerial photographs, but those are all examples of ways that we can actually study how glaciers have changed over the past 50, 60, 70 years or so. And the most important part of all of this is that all of the images from the sensors in this box are free. They are freely available for anyone to go and download, starting with, again, all of the different Landsat satellites that have been acquiring imagery since the early 1970s. The French spot satellites are also now freely available, and then there's other ones like MODIS and Sentinel that you've probably also heard of more recently. But what we can then start to look at is how things have changed over that time period. So this is a time lapse of the Columbia Glacier in Alaska. This is a marine terminating glacier, which means that the end of the glacier as it flows down out of the mountains is in tidewater or is in ocean water. And you can see starting from the very earliest image, going back to, or going up until almost today, this glacier has retreated quite a lot. So starting out again about here in 1980 up until today, going up there. And in the last 40 or so years now, it has retreated over 20 kilometers, so again, about the distance between us and Derry. In that period of time, it has also lost over 50% of its volume, which is about 160 cubic kilometers worth of ice. And it has also split into several branches. So you can see how once it gets through this confluence here, we have a big branch of the glacier here. We have smaller branches here that then have further bifurcated or further separated into other branches. So the number of glaciers is increasing, but the size of glaciers is a different story. And by itself, Columbia Glacier has contributed at least several millimeters to global sea level rise. So this is just one glacier that has retreated an awful lot as a result of some different processes that we won't get into. But I want to talk about a different satellite. So all of those images were Landsat. So this is, again, the longest lasting satellite program that we have, starting, again, from the early 1970s. I want to talk about ASTER, which is a sensor that was jointly developed by the Japanese Space Agency and NASA. And it was launched in December 1999 aboard the Terra satellite, which is shown here. And you can see there are a number of different sensors labeled on this diagram. So ASTER is extremely useful because it has the capability to measure topography. So it has two cameras. One is pointing straight down. One is pointing backwards at about 28 degrees. And that means that as the satellite orbits over the Earth, it is looking at the Earth's surface from two different angles. And we can use the principles of photogrammetry to work out what the elevation is. And most importantly of all, from April 2016, the entire ASTER archive is freely available. This is millions of images showing everything all around the world. This was, again, a global mission. And we can use this to construct a 20-year time series of global elevation and also elevation change. And that's what we're seeing in this slide. So this is Iceland. All of the glaciers in Iceland are shown here in the different colors. Yellow is just no elevation change. Red is negative elevation change. Blue is elevation gain. And I'm focusing in here on a few glaciers down here in southern Iceland. And this animated GIF, which you can see is ticking down, is actually showing some of this time series. So we can actually watch, starting from the early 2000s, how the elevation over glaciers is changing. It's not as simple as this, but this is at least a nice way to visualize what we're actually looking at. So, if we do this for all of the glaciers around the world, remember I said that's about 700,000 square kilometers, we take all of the ASTER images that we can, we process all of them, and then we add up all of those elevation changes. What we end up with is a picture of the volume and mass changes for all of the glaciers around the world over the past about 20 years. And so this was some work that we published a few years ago that shows this. And so you can see, starting up in the top here, you can see Alaska, glaciers in Alaska and Northwest Canada are contributing by far the most in terms of glacier mass loss at about 66 gigatons per year. Globally, glaciers are losing about 266 gigatons per year. And so, before we go much further, I need to explain what a gigaton is. So a gigaton is just 1 cubic kilometer of water. So when we melt the glacier ice, we convert that into water. 1 gigaton, so 1 billion tons, or sorry, 1 billion kilograms. Did I have that right? No, I think that was 1 billion tons. Anyway, it's about 1 cubic kilometer worth of water. Or, if you prefer, about 76 times the volume of Loch Ness. Or, if we were to spread all of that water out over the surface of the island of Ireland, we would end up with about 3 meters worth of water covering everything. So this is a lot of water, and this is happening every year over the past 20 or so years. This is about 1/5 of the observed sea level rise over that same period of time, and it's also accelerated. So between 2000 and 2010, it was closer to 200 gigatons per year, and between 2010 and 2019, it was closer to 300 gigatons per year. So we've actually seen an acceleration over the time period that we were looking at these changes. Which brings us to another point that we talked a little bit about in the previous presentation, and that is that glaciers are extremely important water resources. So glacier melt helps to delay the runoff peak in river catchments. So this graph here, the green line is an example of the flow over the course of the year in the River Seine, which is almost entirely fed by rainfall. The blue is the Dnieper River in Ukraine, and that is primarily dominated by snowmelt. And so what you can see is that the Seine, there's more rainfall in the winter months, and so you see a bit more flow, but overall it's fairly even. The Dnieper River, we see that there's a big spike in the spring when all of the snow starts to melt, and then it drops off later in the year, and there's a lot less flow available. And then the orange is the Rhone glacier catchment in France. And you can see that compared to the snow melt-dominated catchment, it actually shifts the peak to later in the year. So we have more flow later in the summer, in the hotter months, and into the autumn as a result of this delay. So glacier ice catchments can be very important to help sort of spread those water resources out over the course of the year. And a good example, and thank you again for the introduction, is in Central Asia, where about 800 million or so people depend on glacier meltwater for all sorts of things, including basic water resources. Now, in normal years, precipitation is the dominant contribution to river flow. So the pie charts here in this map show you the size of the pie chart tells you how much water there is. So of course, the Indus River, which we saw quite a bit of, is quite large, but there are lots of other smaller catchments. The light blue color is the indication of how much of that is precipitation. The darker blue colors are indicative of how much of that is glacier melt. And so you can see that in normal years, most of what we're seeing flowing through these rivers is rainfall. In drought years, we see first that the size of the pie chart has shrunk, right? So there's less water available overall, but glacier melt has actually expanded to be a much larger portion of the available water. So it helps to buffer some of that drought stress that's occurring. And so as we're seeing more and more glacier melt, what we are seeing is that at least in drought years, there is a little bit of an offset. However, what happens when we start warming the climate, right? Because that's obviously an important question that we're kind of talking quite a bit about today. So at first, more glacier melt means we have more runoff, right? So we're melting more water, there's more water flowing through our river systems, and so you end up seeing that there's this actual increase in the amount of discharge over time. Eventually, though, like a bank account where you are spending and spending and spending and spending, we end up passing through something that we've called peak water, which is where we have the peak of that discharge curve, and then it starts to go down again. And so we actually have less water available overall because we've now completely depleted the glacier reservoirs. And thinking again about the changes from going from a glacier-dominated system to a snowmelt-dominated system, we are also changing the timing of that melt throughout the year. So if we were to look at all of the very large, so more than 5,000 square kilometer river catchments around the world that have glaciers in them, and this was a study from 2018, what they found was that 45% of those different river systems have already reached peak water. So they've already passed through the point where we see increases as a result of more glacier melt, and we're now starting to go into the decline. So the example on this graph is the Rhone catchment, which we already saw. And the other 55%, we expect to see peak water at some point before the year 2100. So this is the Aral Sea Basin in Central Asia. And you see that the peak is expected here somewhere around 2050 or so. But glaciers are also extremely important habitats. So this is a picture I took actually out in front of Columbia Glacier, which we saw from above earlier. It's way back here in the background, and you can actually see the tan mountain sites here. This is actually a direct result of the rapid changes that we saw. So that's about 300 meters of thinning at that sort of central location there. But glacier fjords also have lots of fish. They're home to lots of different bird species. They're home to mammals such as sea otters and seals. They're home to mammals that eat seals and sea otters, like orca whales. And they're also important for humans because we use them as fisheries. We use them for all sorts of other things. Tourism is obviously another big part here. So glaciers are really important from that respect. And so we're looking now at a schematic showing the Kronebreen, which is a glacier, a marine terminating glacier in Svalbard. And in a marine terminating glacier, meltwater actually enters the fjord system from underneath the glacier. So it's flowing out under the glacier into the fjord. That water, of course, is extremely cold, and it is also fresh water. It contains sediments, and because it's cold and fresh water, it upwells. So it causes upwelling as it exits the glacier because it is less dense than the saline water that it is replacing. And so what that means is that zooplankton, like the shrimp I think that they've shown in this example here, zooplankton actually get caught in that upwelling plume, and they bring birds. Because birds have figured out that where they see these upwelling plumes, there's all sorts of really easy to pick food available as a result of this, of these different physical processes. So this is another great example of how glaciers, again, are really important habitat, not just water resources, not just sea level rise. So let's take a little bit of a step back and look at how glaciers actually work. So this is a cutaway schematic of a glacier flowing down out of the mountains. And so I've mentioned earlier accumulation, which is the mass gain. So these are a result of processes like snowfall. This can be snow transport, so snow that blows in as a result of avalanches or winds. We also have ablation, so this is where mass is taken away from the glacier. So this is most often when we're talking about melt, either at the surface of the glacier or the base of the glacier. This can also be calving if the glacier is marine terminating or lake terminating. So if the end of the glacier is in water, it will also break off chunks of ice, and that carries mass away from the glacier. And in some places, we also see sublimation being an important mass loss mechanism. So areas where it is extremely dry and warm during summer months can also see a fair amount of sublimation as an ablation mechanism. And then mass balance is just the difference between the mass that is put in and the mass that is taken away. And we also have something called the equilibrium line altitude, which is the elevation on the glacier where the mass balance is equal to 0. And we often use this as a proxy for understanding how climate affects glaciers, and we'll see an example of that in a minute. What time is it? No, what time is it? Okay. We might not. So the other thing to remember is that glaciers flow. So we have mass being added up here at the top, we have mass being taken away down here at the bottom, and that's part of what causes glaciers to flow from higher in the mountains down below, the other big part of that being gravity. But this ends up redistributing mass from higher to lower, which also means that you're moving mass to an area where you tend to lose it more. Okay. So we'll very briefly run through this because I know everyone loves math. But in science, one of the things that we're really trying to do is understand the world around us, explain how it works, and also make credible predictions. And one of the big tools that we use for this is a mathematical model. So we take some kind of input, we do some kind of math or maths on it, and we get some kind of output. So we'll look at a very simple example here, the surface area of a pizza. So if we assume that we're running a pizzeria and we want to understand or want to be able to model how many toppings we need to order, we need to think about how many pizzas we're going to make. We need to know about the size of those pizzas. So we want to understand what the surface area of the pizza is. And this has to be really simple, right? Pizzas are pretty round. So we just measure the radius of the pizza. We use the very easy to remember formula for the surface area of a circle, and that's it, right? That was easy. But what did we forget? What's that? Distribution. Distribution is a good point. Yes, I didn't think about that. I thought about the crust, right? We don't typically put toppings on the crust. We want to keep it in the middle of the pizza. So we have to take that into account. So, okay, fine. We subtract away the thickness of the crust from our radius of the pizza, and there we are. Except crusts aren't even thickness most of the time unless you're really, really good. Your pizza isn't going to be perfectly round, again, unless you're really, really good. We have to think about the distribution of the toppings on the surface of the pizza, and so on. So all of this is to say that, generally speaking, all models are wrong in that they make some kind of assumption or simplification, but we can still learn something from them. So for example, this would actually be a pretty good approximation for the surface area, unless you're making a square pizza, in which case you'd have to think about square pizzas instead of circular pizzas. There we go. So, moving to a slightly more complicated example for glaciers, we have different inputs. So one of the inputs that we use is, for example, meteorological data. So this is temperature, this is precipitation. Sometimes we measure a lot more than that, but those are the two big basic ones that we can think about right now. We also need to put in the glacier thickness because that tells us how fast the glacier flows by and large. And we also might want to think about glacier mass changes. So we use our observations to help us figure out how our model should work. And then the maths that we do is often we need some way to model how glaciers flow. We need some way of modeling how glaciers lose mass. So we need to figure out how to model the ablation or the melt. And we need some way of measuring the mass gain, so how much snowfall is coming on the glacier, how much of that sticks around, if it's blown away by wind, etc. And then the outputs that we get from this, of course, are the glacier mass at some future point, the glacier area, and sometimes we also study how fast the glaciers are flowing based on these different models. So that's a very quick, simple overview of how we actually do glacier modeling. It's just different inputs, different math, and then we look at the outputs that we get. And so this video was put together, again, by some colleagues in Switzerland. We're looking now at the Aletsch Gletscher, and we're looking at it under 3 different scenarios. So we're looking at regional warming up to 2 degrees above pre-industrial conditions, 2 to 4 degrees, 4 to 8 degrees. And we can see what does the glacier look like in 2100 based on these different scenarios. And so you can see how in the faster warming, of course, we end up seeing a much faster retreat starting in about 2050 or so, and a very rapid loss of the glacier. It kind of breaks up into smaller catchments up there, and under the warmest scenarios, it actually almost completely disappears. And again, this is the largest glacier in Europe, and so when we're talking about up to 8 degrees warming above pre-industrial levels, this is the kind of scenario that we're thinking about. So if we do this now for all of the glaciers around the world, this is a very complicated plot, and I'm not going to go into too much of the detail, but the slides will be available. But the y-axis here shows us the percentage of mass that is remaining relative to 2015 at 2100, based on a whole range of climate scenarios and a whole range of glacier parameters. And then the x-axis here tells us the global glacier temperature change, the global mean temperature change above pre-industrial levels. And so you can see that overall, glaciers are slated to lose somewhere between about 20% and 40% of their mass by 2100 under the 1.5 degrees Celsius warming scenario up to the 4 degrees Celsius warming scenario. So that would contribute up to 154 millimeters sea level equivalent. And it also means that we're looking at between about 50% and 83% of all glaciers completely disappearing as a result of this warming. If we look at this just with the COP26 pledges, that means that we're looking at about 2.7 degrees warming by 2100, and that would mean that we're looking at about 115 millimeters of sea level equivalent melt from glaciers around the world. And again, this is just glaciers. This is not including ice sheets. If we look at the European Alps, in particular down here in the lower left-hand corner, we see that even under the best case scenarios, only about 20% of the glaciers in the European Alps will remain by 2100. And more likely, we're looking at a lot less than that as a result of, again, the lack of action on reducing emissions. So I won't do the example that I was going to do here, but again, the slides will be available and the links are all in the slides. But this is it started as a glacier model, so the Open Global Glacier Model, or OGGM. And they have put together a lot of very cool resources for educators on their website, including a glacier gallery where you can go and look at pictures and other information about different glaciers around the world. There is a glacier simulator where you can actually run your own glacier model, see how different changes in climate impact how glaciers develop. You can also look at how that impacts the mass balance simulator, or the mass balance of the glaciers, and you can also look at information from a range of models about the future evolution of glaciers, so similar to what I had on the previous slide. And there's a lot more there. So this is a very, very cool website that I encourage you to take a look at. I also have a bunch of other examples of different resources that you can look at. AntarcticGlaciers.org is an amazing website with all sorts of information about glaciers, ranging from the very small to ice sheet level. It has information about paleoglaciers, about glacier geomorphology. I mean, it's an astonishing resource that you should definitely take advantage of if you haven't already. There's a link to some different virtual reality field trips where someone actually put a camera on their back, walked up into the mountains to take some really cool 3D images of the landscape that you can then look at through their viewer. The Irish Quaternary Association has a number of resources as well, as does the World Glacier Monitoring Service, the WGMS. And then the last example, so Sentinel Playground is a website where you can go and look at a whole lot of different satellite images as they're made available, including, and hopefully I did this right, I'll look at this screen instead of the other one. Oh, fine. So this link, as it loads, this is a Sentinel-2 image acquired over Northern Ireland yesterday. So you can go and you can look at the most recent images available from Sentinel. I think they have Landsat on here as well. And then you have different tools here where you can go and change how the images are displayed. You can also, if you click the little generate link here, it'll actually export an image that you can then use in presentations or send to your friends or all of those good things. So, there we are. Anyway, I don't think there's time for questions, but I will be available after the break in case anyone does have them. So thank you so much.